Testing of hypothesis is one of the easy topic within the space of machine learning and statistics. But the terminology that is used in testing of hypothesis is so unique, it is so different that if we do not know the terminology, it looks so difficult to understand. So the underlying concept is easy, but the way we term it or the way the kind of terms that are used, somehow this whole concept looks very difficult to digest and understand. But once we understand the meaning behind that terminology, it will be very easy for us. Let us try to understand testing of hypothesis through multiple examples and multiple analogies so that at the end of it, we are pretty comfortable and confident in testing of hypothesis. Testing of hypothesis is a very simple concept. For example, you want to buy 10 kg laddu for a function. Something is going to happen today evening. You want to buy 10 kg laddu. So you go to a shop, a sweet shop. And usually, if you're buying 1 or 2 kg, generally they'll pack and give you. But if you're buying 10 kg or 20 kg, it will not be ready just like that, isn't it? So you go to the sweet shop for giving an order. You said that I want to order for 10 kg laddu and I want it by evening. But the shopkeeper, he told that we already have 10 kg available. So we already have this 10 kg available. Please, you can take it right now. What are you going to do? Tell me. Forget about statistics and so on. Somebody gave you 10 kg laddu on the spot. Are you going to take that whole laddu parcel with you? What are you going to do? Tell me if you are in that situation.
At first, we taste the laddus.
So that means I have some doubt about this 10 kg laddu. I'll ask him to give me one laddu. In fact, he himself will say that, if you have any doubt, please taste it. And then we taste it. And the laddu is super good. It tastes super nice and it tastes so fresh and everything. Then we'll say, go ahead, pack it. But if you taste that laddu, as soon as you put it in the mouth, you felt like vomiting. Are you going to think that maybe that is just one laddu, remaining all laddus would have been good? Are you going to take that whole package, thinking that whatever one laddu that you took, maybe bad one, remaining ones would have been good? Or are you going to reject this whole 10 kg laddu? What are you going to do? Are you going to take that 10 kg laddu from that shop? You're not going to take them, isn't it? So this whole process is known as testing of hypothesis. So if we want to buy 10 kg laddu, this 10 kg laddu is known as, that whole 10 kg is known as population. On the population, we have assumed, like before eating, we are assuming that the whole sweet, the laddu is really good. You have assumed something. That assumption is known as hypothesis. You are hypothesizing. What are you hypothesizing? What are you thinking? The laddu will be good. This is also known as null hypothesis. Whatever you are making as an assumption on the whole population is known as null hypothesis. What is the null hypothesis? We are assuming the laddu is good. Then, are we going to accept this hypothesis, laddu is good, on the population? No. To accept or to reject it, we have done a test. What did we test? We took a sample of it. So we took one laddu. That one laddu is known as sample. Sample is one laddu. What is population? Sample size is one laddu. What is population size? Tell me in this scenario. Try to participate, everyone. Be active. What is the population size?
10 kg.
10 kg is the population size. One laddu is the sample. Now that testing is called test statistic. We have done some testing that is known as test statistic. Finally, based on the test statistic results, we are going to do an inference. What is our inference? Whether the whole population is good in taste or whether the whole population is not good in taste. Are we going to eat that whole 10 kg laddu to test whether it is good or bad, or are we going to take a sample out of it? Based on the sample, we are making an inference on the population. Based on the sample, we are making an inference on the population. This whole process is known as testing of hypothesis. Imagine if we want to buy 10 kg laddu, that is the whole population. We first assumed that the laddu is good, that is known as null hypothesis. We took a sample to test it, that is known as sampling. And then we tasted it, that is known as test statistic. Finally, we took the decision, that is known as inference. That is intuition example 1. Let us take example 2. Let us suppose you are a quality check manager. Now there is a soap factory. Let us suppose you are a quality check manager in Mysore Sandal soap factory. Every day, 1 million soaps are being produced. Every day, 1 million soaps are being produced. Now, every soap has to precisely weigh 250 grams. Now, for 1 million soaps, we do not have a big weighing machine that we can check within one shot whether everything is 250 grams or not. 1 million soaps are being produced. Now, as a quality manager, you have to make sure that every soap is exactly 250 grams. If it is very much less than 250 grams, maybe it is a profit for company, but the consumer will actually sue our company. That may be a huge loss. Obviously, if the soap is more than 250 grams, that is definitely a loss, because we are saying that 250 grams, but we are giving 260, 255 grams. That is on a 1 million scale. That will be very, very big loss. Now, how do you test? Now, as a quality manager, how are you going to put that stamp saying quality check done, 250 grams done? Are you going to go through each and every soap? Are you going to do the weight of that? What will be your process? Imagine yourself as a quality manager in that factory. Tell me what will be your process. What is the population size here?
1 million.
1 million soaps, right? Then you have to take the null hypothesis. What is the null hypothesis? First, you start with an assumption. Tell me what is our basic assumption that we will go ahead with.
Every soap
Okay,
is 50 grams.
250 grams to hoga hi. Let's say, yes, I assume, I agree that 250 grams definitely it would have been there. Then after null hypothesis, to check, to test this null hypothesis, whether this is correct or not, what are you going to take next? Next step will be what?
Sample.
You take a sample. Maybe take a sample of 100 soaps or 200 soaps. Out of 1 million, let us suppose I took 100 samples to 100 soaps I have taken to test it. Then test statistic. What is test statistic? For all these 100 soaps, I will find the average weight. Average weight is the test statistic, X bar. Let us suppose the average of 100 soaps, is 270 grams. The average of 100 soaps is 270 grams. And the null hypothesis is 250 grams. Are you going to approve this lot by putting a stamp quality check passed, or are you going to reject this lot?
Reject.
Because see, if the average of 100 soaps is, let us suppose, 249.9 grams, what are you going to do?
Can approve it.
So a little bit of deviation is fine. Yes or no? 0.1 gram deviation. You don't really care. That's very, very light. Nobody will be able to find it. But 20 grams deviation is high. So that means it can deviate from our null hypothesis, but it should not be deviating too much. If the sample average is 270 grams or 230 grams, you will actually reject the null hypothesis. If it is very nearby, you will accept the null hypothesis. Once again, the population is 1 million soaps. We have assumed the null hypothesis. What is the null hypothesis? 250 grams. We took a sample. We found the average weight. That is known as test statistic. Finally, we ended up in inference. So what is statistical inference? Testing of hypothesis. This concept is also known as statistical inference. What is statistical inference? On the population, there is a parameter. On the population, anything that you calculate on population is known as parameter. So on the population of 1 million soaps, I have a parameter. Average weight is 250 grams. Since you cannot do mathematics, or since you cannot access population, sometimes let us suppose if you want to find the average income of every Indian, can you access the whole population of India? Can you go to everybody and take the value from everybody? In some cases, accessing the whole population is impossible. Do you agree with that? Or it may be time consuming, or it may not be worth to access the whole population, or it is impractical. For example, if you want to know fat percentage in milk, and there are millions and millions of liters of milk, are you going to check in that whole milk? You take every liter, find the fat percentage, every liter, find the fat percentage. Is it possible? There are some situations where you must work with sample. Do you agree? From the population, you take a sample. On the sample, whatever you calculate on the sample, that is known as sample statistic. Sample statistic. So what you do is you calculate sample statistic. It has to fall in certain range. If it falls in certain range, you will accept the null hypothesis. If it doesn't fall in certain range, you will reject the null hypothesis that was made on the population. So what is testing of hypothesis? What are we testing? A hypothesis on the population parameter. A hypothesis on the population. Is that statement clear? What are we testing? A hypothesis on the population parameter. What is a hypothesis? What is a hypothesis? A verbal statement, a claim, or an assumption about the population. So whatever you calculate on the population is known as parameter, population parameter. A verbal statement or a claim or an assumption about the population parameter is called statistical hypothesis. In our example 1, in our Laddu example, tell me what is the null hypothesis, or what is the hypothesis there?
Simple.
What is the hypothesis in that
Laddu
Laddu
is
example?
good.
Laddu is good. The taste is good. In our 1 million soaps Mysore sandal soap example, what is the null hypothesis? What was the assumption? What is the claim? What is the assumption about the population that we made, that we started with?
250 grams.
So every soap weighs 250 grams. And how are we testing? Are we testing on the whole population? Are we eating the whole 10 kg laddu? Is that possible? Do you think the shopkeeper will allow that? Just to check whether this is good or not. Can we eat that whole 10 kg laddu there and then decide to buy or not? That is not possible. How are we testing? Using a sample. Whatever you calculate on sample, that is known as sample statistic. So hypothesis testing is all about testing an assumption or a hypothesis that was made on the population using a sample. Let us go into more details now. Imagine a CEO of a national bank. He claims that the employee's average age is 35. A lot of people in that country, they are saying that this particular national bank is employing all the elderly people. They are pretty slow and we don't want to work with them. We want them to be replaced. So there is a small case that was done. What was the case? Somebody has set a petition that in this bank, and this is a national bank, this is a government bank, we want people who can work very actively. But here the people who are working, the employees in that bank are quite slow and they are not that motivated. That is kind of affecting the whole services. So that is a kind of petition that was on the court. Then the CEO of that company, he told that no, whatever petition that was done, whatever was the claim that the lawyer is making, that is wrong. Our bank has an average age of 35 and we have nearly 3 lakh employees right now. We have 3 lakh employees. Our bank's average age is 35. Now, is it possible? This is a national bank. There are so many branches, 3 lakh people. Is it possible to go and check the age of everybody in that 3 lakh population? It's not possible. So what did we do? We want to, like in the court, we want to prove that this claim that the average age is 35 is actually wrong. How do you prove it? Can you go to the population and get everybody's age? Is it possible? Is it practically viable in the limited time? Tell me what will be the process. We take a sample. We take a sample of, let us suppose 500 people. We have done an interview with 500 people, a small questionnaire. And we have to take a random sample, by the way. Can you intentionally take all the elderly people? That will be wrong. Can you intentionally take all the young people? That will be wrong. You take a random sample. Make sure that you do not have any preference. You take a random sample. And then find their age. If their age is near to 35, then we will say that yes, whatever your null hypothesis is, that is correct. There is no evidence to reject it. If the sample average age is lower than 35, then also fine. If it is how far, like if it is far away, very much higher than 35, that means there is something wrong. Then we can actually prove that the statement is absolutely wrong. This whole process, you can actually fight this case using testing of hypothesis. How do you do that? You first assume that the population average age is 35. That is known as null hypothesis. Yes or no? Null hypothesis is average age is 35. The whole population is actually 3 lakh. The whole population is 3 lakh employees. You take a sample of 500 people we have taken. We calculated on that sample, we calculated the mean. Whatever you calculate on the population is known as parameter. Whatever you calculate on the sample, what is it known as? Whatever you calculate on the sample, that is known as sample statistic. The name is sample statistic. You calculated the sample statistic and the average value is 40. Tell me, are you going to accept that the average age is 35, but by mistake, maybe this is just one sample where the 40 will come. Let us approve his claim, or are you going to reject his claim? This is similar to the example of when you ate one laddu, are you going to assume that maybe it is just the problem with one laddu, let us buy the rest of the 10 kg laddu, or are you going to say this is a random laddu that I have taken? If the whole population is good, definitely this must be good. I should not just, doubt this one laddu. Are you going to approve this null hypothesis? Are you going to reject that null hypothesis? Tell me. If the average age on the sample is 40,
Reject.
we are going to reject. If the average age on the sample is, let's say, 35.2, are you going to approve the null hypothesis or reject the null hypothesis?
Approve the hypothesis.
Approve the null. This is okay. Overall 35 on a sample, little bit of deviation is fine. So what is the reason for rejecting? Why are you rejecting? If his claim is correct, if it is truly coming from a population of average age 35, you expect the average age on the sample to be 35 or 35.1 or 35.2 or 34.9 or 34.5. Maybe you accept if it is somewhere between 33 to, let's say, 37. If it is somewhere between this 1 or 2 points, that is okay for me. But if the average age is 40, is it likely that we would get a sample mean of 40 even though the population mean is 35? Is it very likely or very unlikely? Is it really going to happen that the population mean is 35, but you took a sample of 500 people, but they are getting a sample mean of 40? Yes, it may happen, but does it happen regularly, or there is a very, very less chance? If that chance is very less, it's very rare, then we would say that definitely the overall population mean would not have been 40, would not have been 35. So on the sample, if we are getting a very high value as the average age, that means definitely the overall population would have been average age more than 35. Now, how far? How are we going to decide these limits? Now, the final question comes to this. Are you with me, everyone? What is the final question? How far is actually really far? That means if it is 35, well and good, I will accept. If it is 35.3, are you going to accept this null hypothesis? What is null hypothesis? Average age of population is 35. This is the null hypothesis denoted by H0. Are you going to accept this if the sample average is 35.3?
Yes, sir.
Yes.
35.8?
Yes, sir.
Maybe 36?
Yes.
So to a certain extent, you will accept. If it is very far, then you will not accept. Now we have to define statistically how far is really far. What is that limit beyond which I will not accept? So that can be decided by using sampling distribution. Probably the final link in this whole discussion. Sampling distribution. What is a sampling distribution? If you take a sample, overall you have 3 lakh records. From that, if you take a sample, a large sample, usually a large sample is a sample which is having more than 30 records. That is large sample. Let us suppose I'm taking 100 records, 100 records, 100 records. I'm taking a sample of 100 records, 100 records, 100 records, 100 records. From this whole data, I'm taking a sample of 100, 100, 100 records. And I'm finding mean of this sample, average age in this sample, average age, average age, average age. Everywhere I'm finding the mean. And I'm repeating this process infinite times. I'm finding infinite, I'm doing infinite number of samples. That means first sample I will take. And then again second sample, again third sample. Like that, I repeat it infinite times. Every time I find the mean. And then we can find the distribution of that particular mean. And the distribution looks like this. The mean distribution of all these samples will have an overall mean which is equal to population mean. The average. Sometimes the average will be, for a sample, the average age can be 48 also. Is that possible? Think about it. If you are taking infinitely many samples, for a sample, infinitely many means, let's say you are taking 4 million, 5 million, 10 million samples. If you take 1 crore samples, for a sample, the average age could be very high. Is it possible? Think about it.
Yes, sir.
There is a chance, but very less likelihood. For a sample, the average age will be 25 only. Is it possible? Out of 1 crore samples, can there be a sample where their average age is 25 only? Is there a possibility?
Yes, sir. Possible.
There is a possibility. So like that, and most of the times, what will be the average age? Most of the times, what will be the average age? For most of the samples, average age will be near to
35.
35. So that is what happens. Most of the times, the average age will be near to the population age. Whatever is the population average, which is denoted by mu, most of the times it will be near to that. This is known as normal distribution. What is the normal distribution? Around the average, a lot of values will be there. If you're going far away, far lesser than, far higher than average age, the probability is very less. Is it possible that there is a sample, their average age is just 20? Is there a possibility for it? You have taken a sample, their average age is just 20. Is there a possibility for it?
Yes, sir. Possible.
There is a possibility, but how possible is that? What will be the probability? Can I say it will be very, very less likelihood? That means you have picked a sample where all very, very young people were picked. Maybe there is a possibility, but very, very less likelihood. There will be a sample where the average age is exactly 59. You have taken 100 people, their average age is 59. Is there a possibility like that?
Yes, sir.
There is a possibility, but very, very less possibility. So where will be the highest probability? The probability of happening 35 as the average or near to 35. Like whatever is the population mean. If the population mean is 35, then on the sampling distribution, a lot of samples will have an average age of 35. Are you getting what I'm trying to say? The concept of sampling distribution. The sampling distribution, this theorem is known as central limit theorem. What central limit theorem says is, if we take a sample from a population with the mean mu, then the sampling distribution will be a normal distribution. What will be the mean of sampling distribution? The mean of all these means will be equal to the actual population mean, and the standard deviation is this much. So based on this, what I'm going to do is, I'm going to take 95% limits. 95% of the times, where does my sample mean stays? That I will take it. Now beyond 95%, whatever is beyond 95%, if my sample mean falls in there, I'm going to reject null hypothesis. When are you going to reject null hypothesis? If it is falling within the 95% limits, using central limit theorem, I can get the 95% limits. Let us suppose if the average age is 35, the 95% limits are, let's say, 33 to 37. So when are you going to accept? If the sample average age is 35.3, are you going to accept it? 35.3?
Yes.
If it is 35.9, are you going to accept it?
Yes.
If it is
Yes, sir.
35.95, we will accept. If it is 36.8, are we going to accept it?
Yes, sir.
Yes, sir.
36.9,
Yes, sir.
Yes.
37.1,
No, sir.
37.1 we will not accept, because according to our sampling distribution, if it is really coming from a population of mean 35, 95% of the times, where in which range it should stay? Or sample mean 95% of the times it should stay in which range? It should stay in the range of, according to central limit theorem, it should stay in the range of 33 to 37.
37.
So remaining times, that means even if we have a doubt that maybe the sample that I have taken may be wrong, we will not have anything like that, because we have the central limit theorem which says that whatever is your sample, 95% of the times it should stay here. Do you agree? Is there a dependency on the sample? No. That means if the shopkeeper is trying to tell you, madam, only this laddu is the problem, but the remaining all are good, are we going to approve that statement? Tell me. We will
No.
not. Because according to our central limit theorem, we have some limits. No matter, like, do you think central limit theorem considers all type of samples? Infinitely many types you have taken. Does it cover all type? Like you have taken 1 crore samples. Isn't that a good sample? 1 crore times you have repeated this process. That is why we are going to believe it. So in short, what we are doing is we are starting with an assumption. You select a random sample. You do a test. That is known as calculate the test statistic. If the sample is taken from the population, then you expect the sample statistic to be within certain limits. Have you understood this statement? If the sample is taken from a population, then you expect the sample statistic to be within certain limits. If it is beyond those limits, we reject our assumption. Is this process clear to you? This is the critical statement. If the sample statistic is taken, if the sample is taken from a population, you expect the sample statistic that you have calculated to be in certain limits. If it is not, then you reject the null hypothesis. Does it make sense? Let us go
Yes,
through
sir.
it once again. You make an assumption. State the null hypothesis. Select the sampling distribution. Select the critical region. Critical region means this is the region. If the value that you calculated on the sample, if it falls in that region, then we reject the null hypothesis. So first, you make an assumption. Step 1 is make an assumption. Make an assumption that you are taking a random sample. Make an assumption. And then state the null hypothesis. The basic statement. Have you now understood what is this hypothesis? In simple terms, hypothesis is just a statement. Okay? Make a statement. Then there is something called alternative hypothesis, which is like opposite of that. Null hypothesis is average age is 35. Alternative hypothesis is average age is not 35. Step 3 is select the sampling distribution, establish the critical region. What do you mean by selecting the sampling distribution, establishing the critical region? If average age on the population is 35, then you first find out the limits. What are the limits that you're going to accept? What are the limits that you're going to reject? Based on the sampling distribution, we can find it out. Then you compute the test statistic for the sample. If the test statistic value is falling beyond your limits, then you reject the null hypothesis. So make the decision. How do you make the decision? If everything is fine, you expect the null hypothesis to be in certain limits. You expect the value that you calculated on the sample to be following or falling in these limits. If it is falling beyond those limits, then you reject the null hypothesis. For example, you expect your value to fall from here to here, but it has fallen here. In this case, it has fallen here. Are you going to accept the null hypothesis? Are you going to reject the null hypothesis? If the blue line is the line that is falling, that is where your test statistic is falling. Are you going to accept the null hypothesis? Tell me.
No.
When do you accept? If it is somewhere below, before here, if it is somewhere here, are you going to accept? If it is somewhere here, all this we will accept. But if it is falling very far away, then if it is very far away from our expected region, then we reject. Now to accept or reject, we have another trick. What is it? You can calculate the probability of having this blue value or beyond this. From here, the probability will be very less. Do you agree? If it is falling far away, the probability will be very less. That p-value, that probability is known as the p-value. If the p-value is very less, does it indicate the test statistic? The test statistic is far away. If it is far away, what does that mean? Inference wise, are you going to accept the null hypothesis? Are you going to reject the null hypothesis?
Reject it.
You reject the null hypothesis. So based on the p-value, we accept or reject the null hypothesis. If the p-value is very less means less than 5%, less than 0.05. If the p-value is very less, that means less than 5%, less than 0.05. What does it mean? Try to participate, everyone. It means the test statistic is far away or nearby? Is far away. If the test statistic is far away, what you have to imagine in your brain? You have to accept or reject the null hypothesis.
Reject
Reject the null hypothesis. Testing of hypothesis is used in multiple places where you do not want to access the whole population, where you want to take a sample and then based on that you want to make a decision. Testing of hypothesis mostly a research concept. In the research, it is not possible to access the whole population. We would like to work it on a sample. Most of the PhD candidates, is it possible for them to access the whole population? Recently, Dev sir has completed his PhD and he has done a PhD on telecom mobile operators. Why people switch from one mobile operator to other mobile operator in India. Now, is it possible for us to go to every person who has switched from one mobile network to another mobile network and take their opinion? Is it possible? The whole Indian population that would have shifted is maybe 20-30 crore people would have shifted from one network to other network. So we have to take a sample, but we have to make sure that this sample is from the whole India. So luckily, what did he do? He has taken from his network, from the students, most of our students are from whole India. He has taken a sample of nearly 1500 records. Now that is the sample. And then you expect these values to fall in certain limits. Let us suppose you have milk. Let us suppose you have some chemical composition. Let us suppose there is a product that has been sold. Let us suppose there is a cold drink. In the cold drink, they have mentioned that the sugar quantity is this much per every 1 liter or per every 10 milliliter. Is it possible to look at that gallons and gallons of cold drink and then test it? No. We take one sample. Are you getting a hang of testing of hypothesis, all of you, the applications of it? Where is it used? It is used when we want to access a sample out of the population. On the sample, we do testing. Finally, your decision is made based on the p-value. How p-value is calculated or what is p-value? P-value is that value where the probability of getting this particular test statistic or even worse than that or even higher than that, if you get whatever is that probability is known as p-value. For example, let us take one example where the test statistic is falling nearby. Let us suppose for an example, the test statistic is here. Now, what is p-value? The probability of getting this number or even higher than this number. Tell me, in this case, p-value will be a higher value or a lower value in this case for this particular exercise? This is whole probability. What is the probability of it? Very higher. P will be greater than 0.05. It will be greater than 5%. From here to this whole is p-value is 50%. So is it possible P will be higher than 0.05? From here to here, that is 5%. So overall p-value will be higher than 5%. If p-value is higher than 5%, that is point number one. Point number two, what you need to imagine? Test statistic is far away or nearby. If p is greater than 0.05. Test statistic is far away or nearby. If p-value is greater than 0.05.
Nearby.
Test statistic is nearby. If test statistic is nearby, are you going to accept the null hypothesis or reject the null hypothesis?
Accept the null hypothesis.
Accept the null hypothesis. So usually people do not pay attention to a lot of testing of hypothesis, what happens in the back end. Everybody looks at the p-value. And from there, we have to imagine like this. Nobody imagines now that we can conduct the theory. If p-value is greater than 0.05, test statistic is nearby to whatever is the expected value that we are thinking. So we will accept the null hypothesis. So in simple terms, we are initially saying that, yes, okay, the overall population average age is 35. I agree to your point. I took a random sample of 500 people. I found the average age to be 40. But this is extremely unlikely that the average age is 40 when the population age is 35. In fact, the probability of this is very much less than 1 in 1 billion cases. So what will we do? So how do I find the probability? Because I have a concept of central limit theorem. From there, because I know that sampling distribution, the mean follows particular normal distribution. The probability of getting 40, if average age is 35, 95% of the times it should stay from 33 to 37. Probability that you will get 40 is also there. You may get 40, you may get 50 also. You may get average age as 52 or 58 also. But what is the probability? That probability is quite less. If that probability is less than 5%, that means p-value is less than 5%. Once again, let us write those three statements. If p-value is less than 5, if you know this, almost testing of hypothesis is done. That's why I'm repeating multiple times. If the p-value is less than 5%, what we need to imagine? We have to imagine this normal graph. And then from there, what is our next statement that we will write? If p-value is less than 5%, the test statistic is
Rejected.
far away, isn't it? If the test statistic is far away, null hypothesis is rejected. These are the three statements that we have to imagine. Let's say if the p-value, what is the second set of three statements? If the p-value is greater than 5%, that means test statistic is nearby. If it is nearby, we will accept the null hypothesis. So that is the p-value. So what is p-value? if the observed, whatever we have observed, statistic happened to be just by chance, p-value tells us like what is the probability of getting that chance, what is the probability that you will get that number, or worse than that. The probability of observed test statistic, or even more extreme than that, if it's not, or the null hypothesis is true. That is p-value. P-value is, we got the test statistic to be this number. What is the probability that you will get this number or even farther than that? That is known as p-value. Based on the p-value, we make the decision. Now, if we go back to like, where was the concept of p-value first introduced in our discussions, in our machine learning sessions? Somewhere we have used the concept of p-value. Can you recollect it?
In regression.
In regression. And in which concept we have used within regression?
We are calculating p-value which is the variable is target variable or not.
So when did we use the p-value? What was the use of p-value in regression? What was the problem that we have solved using p-value?
Sir, when we just find the impactful of the variable in the equation.
Right answer. We wanted to find out whether a variable is, let's say xk is a variable, whether it is impactful or not impactful. That is what we wanted to find out. So what happened in finding out impactful or not impactful? The theory behind that is, we first start with a null hypothesis. The null hypothesis is beta I is equal to 0. There is a variable xi, whether it is impactful or not, its coefficient is beta I. If you say beta I is equal to 0, that is your null hypothesis. That means what are you imagining? For a variable, coefficient is 0. By that, is it impactful or not impactful? If you are making the coefficient of a variable as 0, you're taking away that variable. Can I call this as the null hypothesis is, what are we imagining? No impact. Does it make sense? Look at this, all of you. The null hypothesis is beta I is equal to 0. What do you mean by beta I is equal to 0? The variable xi, the coefficient value is 0. For a variable, if the coefficient is 0, that means the variable doesn't exist. That means the variable has no impact. That is the null hypothesis. What is the alternative hypothesis? Beta I not equal to 0. It is not 0. That means the variable must stay. Maybe it is 5 or 10 or -5 or whatever. So the variable is impactful. That is the alternate hypothesis. And then a test statistic is created. And then testing is done. Finally, we get some p-value. Now, based on p-value, we make our assumptions. For example, if the p-value is 0.023, which is like less than 5%. The example that we saw was 0.002, very, very less value. If p-value is less than 5%, according to our discussion in testing of hypothesis, what is the next statement that we have to imagine? This is statement 1. P-value very much less than 5%. What does this mean?
It is far away from
Far away. Test statistic. Tell me the statement. Test statistic is far away. If it is far away, what do we do?
Then we reject the null hypothesis.
Reject null hypothesis. What are you meaning by reject null hypothesis in regression here? What is the statement that you are rejecting? What is the null hypothesis? What is the null hypothesis?
Variable is impactful or not.
What is the null hypothesis? Null hypothesis is this one. Beta I is equal to 0 is null hypothesis. Variable is impactful or not impactful. So here we are assuming that the variable is not impactful. You're rejecting not impact is what you are rejecting. Then what are you accepting? You're rejecting the fact that the variable is no impact. That you are rejecting. Then what are you accepting? The variable is having impact. So finally, p-value less than 5%. Finally, what are we accepting? The variable is impactful. Let us take the opposite of it. Let us suppose if I'm saying if the p-value of a particular variable is 0.30. What is our second statement from there? P-value is 0.30.
It is nearby.
Greater than 0.05. That means it is nearby. The statistic is nearby. If it is nearby, what will we accept? We accept the null hypothesis. Now here, null hypothesis is this. What is the statement that you're going to make? What are you going to accept? You're going to accept the variable has no impact. So if the p-value in regression, if you go back there, greater than 0.05, what were we doing in that case? P-value greater than 0.05. The variable is impactful or not impactful?
Not impactful.
Not impactful. Have you understood why that has happened? Because of this theory behind the scenes. If the variable is having p-value less than 0.05, what do we say back then?
Impactful.
We used to say impactful. Why it has happened? This is opposite of this, less than 0.05, far away. That means we are going to reject this. So it's a kind of little opposite is happening here, but finally the theory Finally, the way it is happening here is if it is greater than 0.05, we are like our whole null hypothesis here itself is about non-impact. And then the central limit theorem comes into the picture. And then based on that, we are saying that if the p-value is greater than 0.05, the variable is not impactful. The variable having p-value less than 0.05, the variable is impactful based on this whole discussion that is happening in the backend. That is how we can connect our theory to whatever we have seen in regression. Now, it is not true that every time you get the right answers from the testing of hypothesis. At the end of the day, you are making the decisions on the population based on a sample. It may happen that there are some errors that you are making based on this sample. Is it possible that your inference may be wrong sometimes based on the sample? It
Yes,
may
sir.
happen that whatever sample that we have taken, that has actually the issue. But we want to reduce it. We want to minimize it as much as possible. Yes, it may happen that some people may have higher age. Some people like this is genuine, that even though this is 35, there can be some samples which are having 58 as an average age, but we are okay to take that risk because overall 95% of the times I want to be accurate. 95% of the times it is accurate. So there are some errors that are possible. For example, there can be some error that after testing, somebody might say that like you are not pregnant. After testing, somebody might say that like because you are just doing a test, you're not really looking at the whole population. Somebody may say that you are pregnant. So if you are rejecting the null hypothesis wrongly, this is a null hypothesis, but I wrongly rejected null hypothesis. That is known as rejection error or the type 1 error. If you are accepting the null hypothesis, so I'm pregnant is the null hypothesis. If you are accepting the null hypothesis, that is known as wrongly accepting null hypothesis is known as type 2 error. So type 1 error is when the null hypothesis is correct, but we rejected the null hypothesis, that is type 1 error. When the null hypothesis is false, but we still accepted the null hypothesis, we did not reject the null hypothesis, that is also error. We would like to reduce as much as possible both of them. We want to make sure that none of them are very high. It is true, we have to be prepared while we are testing. We cannot say that on my test I am 100% accurate. We can only say that 95% of the times, these are the 95% limits. 95% of the times I'm accurate. Remaining 5% of the times I'm taking a chance. We have to be prepared for that 5% error rate. That is all the theory. Maybe once we do one exercise, then we will get one idea. Let us do one quick exercise to get a better idea. There is a data set that has been given by Roseman Store sales data. This is one of the real data set, and Roseman Store is one of the store in US, very long chain. Okay. Now they have given us a very large data set. Every day there are so many customers that will come in. But here what we want to do is we want to take a sample of 100 from that data set, 100 days. Now the null hypothesis that we want to test is the average number of customers that will appear in a day is 750. We get an average of 750 customers. That is what the statement. Is that statement correct or is that statement wrong? Maybe you can say that if the statement is correct, we get around 750. Maybe you can say that, no, we get very less than 750. No, we get very higher than 750. In both the cases, we can say that statement is wrong. Okay. So how do you solve this problem? Let us see the example. At the end of the day, you define the null hypothesis. Finally, everything will come down to p-value. Let me write down once again those 3 steps. You got the p-value, you tested, you got the p-value. Let us suppose the p-value is less than 5%. Automatically, you have to imagine what next statement that should come to your mind is p-value less than 5%. The next statement is
Far away.
far away. If it is far away, you will
Reject.
reject. If you remember this, almost in every testing decision, you are going to make a proper call. Okay. So let us try to do this exercise. Let's go back to our code file. The code file is in the classroom. So here is a code file link that I have pasted in the chat window. Let's import the packages, import the data set. This is quite a large data set, but we are taking a sample of 100 records. The code is pretty straightforward. I'm taking a sample of 100 records. Is this code clear, all of you? This code, taking a sample, quite straightforward. I want to do z-test. I want to extract the p-value, statistical test.z-test. Give the data that you have, sales data customers. There is nothing in the x2 that we are ignoring. We are not comparing two means. We are comparing just, we are checking one mean value. And what is the value that we are checking, whether it is 700 or not. Finally, you will get the p-value. And what is the p-value? This is the test statistic value. What is the p-value that you got? 0.0091. If it is 0.0091, automatically what should happen? P-value less than 0.005, 0.05, automatically we will say it is far away. That is why we rejected null hypothesis. What did we reject? The average number of customers is 700. That we have rejected. Now, if I give you a different hypothesis, can you tell me whether the average number of customers is 750? Can you test that? If you want to test the average customer is 750, what is the change that you are going to make in this code?
Value equal to 750.
Value equal to 750. Can you do that and tell me whether 750 average, that is a null hypothesis? Are you going to accept it or reject it?
Rejected.
Still rejected?
Yeah.
That is based on the p-value only we have to do it. So let us try to calculate it. P-value is 9.20 into e power 05. That means 0.4 zeros. After that, 9 comes. So reject the null hypothesis. Now, final null hypothesis that I want to do is null hypothesis. Let's say if I claim my null hypothesis, my assumption is average number of customers is 650. Can you check now? Is that null hypothesis accurate or rejected? Is that null hypothesis accepted or rejected? If the average number of
Accepted, sir.
accepted, if we make it as 650, p-value is how much? 0.19, which is greater than 0.05. Accept the null hypothesis. Are you getting a hang of this, all of you? By looking at the p-value, why people are accept or reject? Can you imagine this in your brain? As soon as you see the p-value, can you imagine that normal graph? On that normal graph, where is your
Yes,
test
sir.
statistic? All of that, like that imagination, if you can have it, then this whole thing will look very simple to you. Why p-value is important? Based on the p-value, how are people accepting or rejecting null hypothesis? There is a simple logic that normal curve is imagined in the backend, and then based on that, we have to see that yes, it is far away. This should not happen. That is why we are rejecting, or that's why we are accepting. So different type of tests are done. So here we have seen one test that is done for checking the single mean. If you want to check multiple means, that is also possible. For example, I want to check whether there is any difference when I'm checking two means. For example, there is a time where we have given promotional offers. There is a time where we have not given promotional offer. Look at the problem statement, all of you. In the Roseman store data, now I'm a manager or I'm a chief operating officer. I want to know, is there any significant difference in the average sales when the promotion is 0? That means when there's no promotion, average sales is this much. When the promotion is 1, average sales is this much. Yes, I see that if the average sales is 2000 here, if the average sales is 2010 here, I see that there is a slight improvement. But is it significant? Have you understood the statement that I'm trying to make? My question is there a significant difference between the average sales when there is a promotion not applied, when there is a promotion applied? That is a question. So how do we solve that? Again, we will go here. We will define the null hypothesis. The null hypothesis is there a significant difference? So initially we will say that there is no difference. There is no difference. We will start with that hypothesis. With that, we will calculate the p-value, and then finally we will say whether we have to accept or reject the null hypothesis, depending on the p-value. So here we are rejecting the null hypothesis. That means we are rejecting the fact that there is no difference. That is what we are rejecting. We are assuming that both the sales are equal. That is where we started, but we reject the null hypothesis. Finally, we accept the fact that yes, there is a significant difference, and that is what will happen if there is a promotion versus if there is no promotion. Obviously, there will be a difference in the significant difference in the sales. We can test the multiple means also. Here, that this test is known as Z test. For testing multiple means, we use something called F test. Whichever is the test, finally, you will use the p-value, and then you imagine that the value is far away or nearby. Then you say accept or reject the null hypothesis. So no matter, like here, we are testing whether these four types, whether these four stores, A, B, C, D, all of them have similar sales or dissimilar sales. So the null hypothesis is we will start with an assumption that yes, all of them have the same sales. Finally, we are accepting the null hypothesis, whether the store is A or B or C or D, all of them will have the same sales. That is what we are accepting. Similarly here, if the day of the week is 2 or 3 or 4, whether it is Tuesday or Wednesday or Thursday, is the sales same or is it different? We are rejecting the null hypothesis. That means initially we started with an assumption that when it is these 3 days, all of them have the same sales. There is no significant difference, but we rejected that null hypothesis. Looks like there is a significant difference between the sales of these dates. Different dates have different days of the week have different sales. So that is the basic concept of testing of hypothesis. Now there is one more test that is very significantly used, the test of independence. That test is known as chi-square test of independence. Apart from the previous test that we have done, there is one more test that is very, very frequently used, or that is chi-square test of independence. That is used to check whether two variables are independent or dependent. Before we go to the actual example, I'll show you a simple toy example to get the better understanding of the concept. Then we will take that case study. Imagine you have two columns. One is gender of the student. The other one is exam result. Let us say this is X column, this is Y column. Gender is male, female, male, female, male, female, that is gender. Exam result is pass, fail, pass, fail, passing, failing. Now I want to know whether these two things are independent or dependent on each other. What do you think? Maybe general conception is like gender has nothing to do with exam result. But if I'm talking about a particular exam, particular set of people, I have to give a proof. We cannot assume anything, isn't it? Based on the data, I have to give a proof. Let me give you one simple scenario here. Imagine there are 500 male students. There are 500 female students, okay, that have attempted the exam. Overall, how many students attempted the exam? 1000 students. And what we observed is there are 600 students who passed the exam. There are 400 students who failed the exam. Now here is the table. Male student, some of them have passed, some of them have failed. Female students, passed, failed. Now tell me, being a male or female, is it independent of passing or failing, or the other way around? Passing or failing, is it independent of being male or female, or gender really impacts passing or failing? In this particular example, look at this table and tell me. Gender and exam passing or failing, are they related to each other in this exam?
Yes.
No, sir.
Not at all. How many male are there? Tell me. How many male are there totally?
500.
500. Out of them, how many have passed?
100.
100. How many have failed?
400.
400. How many female are there?
500.
500. Out of them, how many have passed?
500.
500. How many have failed?
0.
Now tell me, being a male or female, does it have any impact on passing or failing?
No.
It doesn't have any impact? Or it does have an impact? Think about it. All the female have passed. All the male, have they passed?
No.
See, what is the pass percentage? How much percentage of the total? Let us suppose there are 500 male, there are 500 female. How many people have passed overall out of 1000? How many people have passed?
600.
600. That means, can I say 60% of all the population have passed? Yes or no?
Yes.
40% have failed. Imagine being a male, being a female has nothing to do with pass or failing. So out of 500 male, how many should have passed?
100.
How many should have passed? Don't think
It's
about
300.
what happened actually, but how many should have passed? Expected value of pass in male population
300.
should have been how
300.
much? 60% of 500, which is like 300 male should have
300,
passed,
yeah.
isn't it? If
Yes.
everything is fair. How many should have failed?
200.
200. Out of female, how many should have passed?
300.
300. How many should have failed?
200.
200. If there is absolutely no relation between male or female related to passing or failing, this is what your expected table. Yes or no?
Yes, sir.
But what have you observed? What is the observed result? Observed means whatever we have seen. Originally, how many males should have passed? If there is no relation between passing and failing and gender, 300 should have passed. But actually, how many male have passed?
100.
100. Originally, how many males should have failed? Originally, how many males should have failed if there is no relation at
400.
all? 200. But how many have actually failed?
400.
400. Is it very near to our expected values or very far away from our expectations? Tell me.
Very far away.
This is expected value, assuming that they are independent. Yes or no? We assumed that whether you are male or female, that is independent of passing or failing. We have taken 60%, 40% count. Now let's come to female. Originally, if there is no relation between female and passing and failing, how many should have passed actually? How many should have passed?
300.
300. But in reality, how many have passed?
500.
500. How many should have failed?
200.
But how many have actually failed in reality?
0.
Now tell me, male or female in this data set for this exam, being a male or female, does it have an impact on passing or failing?
No.
It does, no. Male people are failing. Female people are passing. Yes or no? It does have an impact. Or these two are independent, passing or failing versus male, female. If they are independent, we should get these numbers, right? If they are independent, we should get, instead of 100 people passing, we should have 300 people passing. Instead of 400 people failing, we should have only 200 people failing. Can I make this statement, male, this particular people are failing a lot? Is that a right statement?
Yes,
Or
sir.
let me tweak this example further. For example, it is not 50-50. Let us suppose male are 500, female are 500. Pass, 500 people have passed. Failed, 500 people have failed. Let us suppose this is what I have observed. Male, female, pass, fail. Overall, 500 people have passed. 500 people have failed. Okay. 500 people are male, 500 people are female. Now, in male, I found that all the 500 have failed, 0 person has passed. In female, all the 500 have passed, 0 have failed. Now tell me, being a male or female, does it have an impact on passing or failing?
Yes, sir.
So the same thing is happening here. Instead of 500 and 0, I have written 400. Here it is 0. So having an impact or not, or whether these two are, if they are independent, if these two are independent, male or female are independent, what would have been that table? Tell me. Overall, 50% are passing, 50% are failing. Can you tell me the numbers inside this table that should have been come out of male? How many should have passed here? What should have been that number? If there is no impact, if both of them are independent,
250.
250 should have been here. Here there would have been 250. Here there would have been 250. Here there would have been 250. If those are the expected values. So what I'm trying to say is, if they are independent, you expect the numbers to be like this. If the numbers are very near to this, then you would say they are independent. If the numbers are very far away from this, then you would say they are dependent. What do you mean by depending? Passing or failing is related to male or female. Male students are failing a lot. Female students are passing a lot in that particular exam. If they are independent, if there is no relation, then the numbers that you expect is this way. So that is known as chi-square test for finding out whether they are independent or not. How do you do that? There is a formula for chi-square test. This is known as observed value. This is expected value. Observed minus expected whole square. If these two are matching, then this whole chi-square will be a very less value. Then you will say that yes, that is independent, because these numbers that you are thinking and matching with these numbers. But here, if it is not matching, if they are far away, then the chi-square value will be very high. That means you will say there is a dependency. Chi-square test is used for checking the dependency between two variables. If chi-square value is very high, yes, they are dependent. If the chi-square value is very much low, they are independent of each other. That means it is near to the table that we have seen as expected table. This expected table is generated based on the hypothesis that there is an independence between these two variables. So finally, we will not really calculate all this. Finally, everything will come down to p-value. Based on the p-value, we accept or reject the null hypothesis. So for example, in our one of the cases, we wanted to find out in this bank marketing data set, I wanted to find out whether there is any dependency between any one of the column versus target. Job is one of the variable. Marital status is one of the variable. Education is one of the variable. I want to find out on my target variable, which is taking 0 or 1. Is there any impact of job on the target variable? Is there any impact of marital status on the target variable? Maybe target variable is customer being a good customer or bad customer, or customer respond or not respond. Customer responding to my call or not. Does it have any relationship with marital status? Does it have any relationship with job? If I want to test the independence of these variables, I will do the chi-square test of independence. Then I'll finally get to know whether to accept the null hypothesis. That means I'll accept that they are independent. So here, null hypothesis in chi-square test. Null hypothesis is independent. Both the variables are independent. Alternative hypothesis is dependent. Both the variables are dependent on each other. So that means when we are rejecting that null hypothesis, then we will say that they are dependent. Reject null hypothesis. That means I can say that the month versus a customer being buying or not buying is impactful. Reject null hypothesis. Previously, whatever is this variable versus the target variable is impactful. Reject. Whenever you're rejecting, you will say that yes, there is an impact of that variable on the target. Okay. So that is the testing of hypothesis. Usually people see this whole process of testing of hypothesis as simply in 2 steps. Usually when somebody says testing of hypothesis, we generally think of a p-value. You have the p-value. Based on the p-value, you tend to accept or reject the null hypothesis. The place where we have seen testing of hypothesis, which may come to you frequently in future, that is the regression and the logistic regression. In these two algorithms, there is a place where we have seen variable impact. If a variable is impactful or not, that we check using p-value. If the p-value is less than 0.05, that variable is considered as impactful because our null hypothesis is non-impact. So we reject the null hypothesis. That means we are accepting that it is impactful. If it is greater than or equal to 0.05, that means the variable is not impactful. We are accepting the null hypothesis, the fact that the variable is not impactful. This is that one line that we have seen when we were discussing regression, and whatever we have discussed right now is the whole, explanation of that one line or one step. So that is the story of testing of hypothesis.